Everybody. So we're live again, and as you can see, it's a little bit different than our usual setup. So if you notice any audio issues, because I had to set up another microphone and we have new headphones and another cable, let us know in the chat if there's any problems. And if you notice that there wasn't a video this morning, that's because this live stream is kind of a big deal, and it's our first time having a guest. So next weekend will be the usual format where in the morning at 11, you'll get a video and then another live stream at night where you guys can ask questions about that video.
Sounds good.
Yeah.
So basically, what we wanted to do here is, as we've suggested over the last couple of videos or live streams, that we were going to be hosting guests, both remotely as well as in person. And it's always nice when you have people in person. And we had the opportunity to interact with a pretty impressive guy who we're going to be doing some collaborative work with in the future. And it happens to be that he had the opportunity to join us for this live stream. And so that's one of the reasons why we decided that we weren't going to try to rush to get the regular video done this morning, and we would spend time getting this set up. So that's what we're going to do. And let me start by introducing Lars and let him tell you a little bit about himself.
Thanks, Eric. Great to be here and to be talking to everybody tonight. My name's Lars, and background is in operations research, industrial engineering, and have been working for 20 or 30 years here in a lot of industrial settings on designing better processes and systems, and a lot of the type of work that Eric and Alex have been involved with here on the channel. And so I'm excited to be here and answer questions, talk about some of the recent videos, talk about other new things in the future. And so it's great to be here. My background's, like I said, all in operations research. For those of you that don't know what operations research is, it is well, when you think about the UPS trucks and finding the shortest route to deliver their packages and always taking right turns, that type of mathematical programming is part of operations research, as well as a lot of probabilistic prediction of how things are going to happen, simulation modeling, things like that. So I've been doing that for 30 years or so, and excited to be here.
Also a background in electrical engineering and mechanical engineering.
Started in electrical engineering and sort of, I guess, a natural mechanical inclination.
As you'll find out.
Rebuilt the engine in my old 1964 Ford Galaxy, my favorite car from all time. And and just lots of...
and at one time you were involved in the construction of the world's highest telescope.
That is true.
Yes.
Yes.
So kind of an interesting thing. And in addition to that, as some of you have kind of surprisingly guessed,
yes.
The reason we brought Lars in specifically for our first guest is because they happen to be driving through. He is my brother-in-law, and we've got some of our other relatives present in the studio. Give us the wave. Yeah, so now we're under some pressure to do well. And in addition to that, even though we're going to be going through the previous videos that we've been handling and answer any kind of science, engineering, and technology questions you have in general, we're going to apply 2 or 3 heads in this case to some of your questions. So hopefully we can provide better answers and maybe approach it from different angles. Also, you have a doctorate in...
I do, a PhD in operations research and a master's from University of Texas, Hook'em Horns, and a PhD from Illinois Institute of Technology in Chicago.
And what we're going to be doing is over the next few months, while Lars is getting into the idea of starting his own channel, and he can tell you a little bit about that, he's going to be collaborating with us on a few pretty interesting topics, one of which we've begun already, and we're going to give you some details about that. I think it's going to be not only pretty interesting, but potentially very, very important globally because of the importance of the availability of water and pure water and how to make sure that you don't contaminate, but at the same time you don't overspend or over-engineer. You know, there was an old saying that anybody can build a bridge, but it takes an engineer to barely build a bridge. And it takes a lot of broad thinking in order to try to minimize over construction, over design, wasteful spending, and all of the ramifications of assembly, maintenance, lifespan, and environmental impact of anything that you do. And so an engineering approach along with a more basic science approach, I think gives a really nice balance to the way that we're going to approach this. And hopefully we don't get into too many arguments. So if anybody's got any questions about any of the previous videos, feel free, because we can both address any questions you have about our most recent video on the air conditioning system. And any questions that you have, we'll try to answer them if we can. In addition to that, one of the things that we thought would be kind of fascinating to cover is when Lars was describing the problem that he was facing. He was looking for some advice about how to deal with a particular issue on his boat. We were talking about the water maker and the water availability function. And I like boating, but I don't know anything like he does about the nature of the systems that support a boat. And water availability, despite the fact that you're floating, is still a big deal. And we were trying to brainstorm and have come up with some pretty good ideas about how to evaluate the best solution for water availability on a boat. But in addition to that, it also applies to water availability at home, in a small house, in a mobile home, in any neighborhood that's, for example, damaged by a hurricane or has power outages. What do you do about availability of water? And how do you evaluate it, and how do you install it? So that's the kind of research we're going to be doing over the next couple of weeks, and working on some projects that we're going to produce videos about. Another thing I was wondering if you might want to cover is a little bit about what we were talking about earlier on, about some of the problems of doing the analysis. When, for example, if you go online, you buy yourself a water purifier, or you buy yourself a reverse osmosis system, what are you actually trying to achieve? Are you trying to make your coffee taste good, or are you trying to protect your health?
Yep.
And in addition to that, how do you evaluate systems, not just based on cost and hearsay? And it's the approach to looking at the system by tearing it apart and figuring out what parts of the system are doing what and how they interact, to decide what maybe is underbuilt or overbuilt, like we discovered with the air conditioner. The fan motor on the air conditioner turned out to be one of the biggest keys to the success of that project, and actually surreptitiously turned out to be perfect for the kind of modification that we made. For example, if you run an air conditioner and you turn the blower down, or you block the internal blower with dirt and debris, the flow through the evaporator coil slows down substantially. And as a result, the evaporator gets colder and colder and colder. Now, if the system didn't have any kind of protective system, you can actually freeze the evaporator and damage it. So with our system removing the heat so much more efficiently because of the water cooling application, we could have very seriously overcooled our air conditioner, and it would have been a failed project, and I would have had to go through it to try to figure out what to do to solve it. As it turned out, by just removing the condenser fan, we blew enough extra air through it to keep the temperature within the operational range. That's not how you engineer things. That's how you get lucky, and most of the time you don't get lucky. So one of the issues that you will have when you're doing any kind of a project where you're going to be integrating different components in the system is, how do you evaluate what the role of that component is as you change it, or as you modify upstream or downstream? How can you produce the loops to analyze this? And then how do you engineer flexibility in, so that you don't invest a whole bunch of money in what you think is a brilliant idea and that it ends up being wasted? So I think one of the things we should approach first is probably a consumer evaluation.
Sure.
Yeah.
Yeah, and maybe a little background on where this whole discussion started.
Yeah.
So I bought a boat recently, and it's a pretty cool boat. It's a 27 and a half foot wooden boat built up in Nova Scotia in 2002. I think Alex is going to run a little video here.
Yeah, I can do that for you.
And how'd you get the boat?
Found the boat, actually, my friend Greg found the boat on Facebook Marketplace down in South Haven, Michigan. And so it wasn't being marketed too widely at that point, which was, I mean, wooden boats don't move all that quickly anymore.
Yeah.
Because there's not too many of us fools that buy wooden boats.
They move slow and they sell
They move
slow.
slow and they sell even slower. But it's an interesting boat. Covey Island Boat Works up in Nova Scotia built it 2002. It was commissioned for a woman who took delivery when she was 83 years old. And at age 79, in her previous boat, a 30-foot wooden sailboat, she solo sailed from Newfoundland to Ireland.
Yeah.
At age 79. Pretty amazing.
Even older than us.
A lot of good karma there. So
Yeah.
it's a little boat. It's a Ted Brewer design called Blue Hill. That's the design. And its name is Kuan Yin, which is a Buddhist goddess of mercy and compassion. And so a small 27.5-foot boat that thinks it's big. It's got a lot of systems on it. But water is one of the issues. And for saltwater water makers that are common and very expensive, those are high power demand, 1 horsepower motor, 800 PSI, very capable systems, but expensive and perhaps a little finicky. My boat is sitting in the Great Lakes. So I'm in fresh water and fairly clean water for the most part when I'm actually out in the Great Lakes. So then the question became 2 things. One, I have 2 water tanks, and I'm not always at the boat rather. So if the boat's been sitting for 4 weeks or something, what's the state of the water when I get back? Right? Has anything started to grow? And then also just water from marinas. All of that can be a little iffy. And so the question just became, can I make water, as it were, filter clean water from the Great Lakes to replenish my water while I'm out and about? Can I, in my words, polish the water that's in my tanks to make sure that it remains clean? And so that started the discussion of commercially available water systems that you can get off of Amazon or fancier ones from places like SpectraPure, and reverse osmosis or just filtration, UV sterilizing. How do we measure the input quality of the water in terms of both metals and whatnot, as well as biological items, bacteria and whatnot? How do we measure that input? How do we measure the output to
know
make
if it's
sure
good?
that it's actually drinkable and safe, right?
Right.
And that was the beginning of the discussion, and it's just blossomed from there.
And the thing about like reverse osmosis, I mean, a lot of you might have reverse osmosis systems. They've come down a fair amount in price. You can get them from SpectraPure even for around cheap, like less than $1,000.
Yeah.
But the point is, the way that they operate is that if you have a filter, a very, very, very fine porous membrane, and you put dirty water on one side and you don't do anything more, it's just going to sit there. But if you want the water to be purified, you want it to be filtered or polished, it has to pass through the membrane. It needs some pressure to do that. The problem is osmosis is the process kind of based on entropy, is that if you have 2 containers of water, one's got a contamination, one is pure, there is a entropic desire of those water molecules to even out. And so water will flow into the more contaminated material. It's drawn into it. And so it will continually dilute the pollution with the idea that eventually it'll become pure. Well, the problem is we want the pure water. We want to reverse the natural entropic process. So you need to use energy to do that. And therefore they need pressure. And I was surprised. I had an old osmosis, reverse osmosis system in my home years ago. I didn't realize that in order to get the pressure to purify this water, you have to go up to something like 30 atmospheres, 20 or 30 atmospheres of pressure to do this. That's why it requires so much power to force the pure water away from the particles it wants to be next to through the membrane and into the pure side. And there are tricks like permeate pumps and other systems that can be used to sort of try to recover some of that pressure investment. But the problem is it does require a lot of power. And one of the questions is, what if you just use a coffee filter? If you can use 1 G of filtration pressure to push the water away from its debris, and you get sufficiently pure water, why bother with all that power? Well, the only way you can know for certain is you have to analyze it. And there's a number of different ways that you can analyze it. For example, total dissolved solids. If you're not familiar with that,
Yep.
I mean, you can explain it or I can explain it, but basically, you just have a couple of electrodes in the water. Absolutely pure water, just hydrogen and oxygen molecules, is a very good insulator. You cannot get current to flow across. Add just a pinch of salt or debris or anything else, and those ions, those particles, can do the conducting. So a total dissolved solids monitor simply measures the resistance of the water, and the higher the resistance, the greater the purity. That's why when you look at deionized water or high purity water, it'll give an ohms of resistance. That's basically what it's looking at, is how close are we to pure water. So do we need super pure water? And if we do, how pure, and how do we know we're getting it? So we're going to be looking at optical systems, light scattering, as well as spectroscopic methods in order to be able to evaluate the purity of the water that comes out. Not that you would install this necessarily in a system that you built, although it may be possible, as I'll get into.
Yep.
But it adds another level of analysis to the simple some particle. You don't know if it's toxic or it's just sodium chloride salt. So that's part of what we're going to be doing, is the analysis of operational systems. And then when we make modifications, do they improve it or do they make it worse? And you can see in just a couple, 3 days and a few emails back and forth, we're already kind of moving into the formation of the idea, the plan for some videos, a video series. And that's kind of the very early stages of how all videos are created. Is you come up with an idea and it survives the problems that you might solve in trying to create it.
Yeah.
Okay, let me interrupt you
Oh,
for
I'm
a
sorry.
second. No, it's fine.
no.
Yeah, no, it's fine. But Awestrike, thank you very much for the 5. It's a question about the AC video, so this is for you. Your AC was very impressive, but I suspect the surrounding Earth takes many hours or days to equilibrate temperature gradients, long-term efficiency.
Yeah, what I've had a couple of written comments about that, but surprisingly few. I would have thought there would have been more about that. What we discovered is that indeed the temperature of the ground, measured by the water flowing out of the ground as sort of a distributed thermal measurement system, rose slowly during the day. At about 8 hours, 8.5 hours, it sort of stopped going up, and it reached 30 degrees Celsius, and it stayed there. Now, to be fair, it stayed there even though now we're into the night, but by the next morning, it was still at 30. By the end of that day, it was still 30. So I think the equilibrium
I did the
The
same thing.
balance.
the balance between the surrounding ground temperature heat flow and the heat input from the air conditioner
Yeah.
is going to be reached in a relatively short period of time. Let's call it 12 hours to 24 hours. One advantage you have in a typical system, unlike ours, the way I ran it, is you're not going to be running it 24 hours a day. Typically, you're going to be running it a lot less during the night, and the heat flow is continuous. So I suspect that our system will remain this way until other influences occur. For example, lowering water content in the soil as the soil dries out over weeks or months, just seasonally. Another little problem is that I think I admitted this in the other live stream, but I think I should repeat this. I didn't design the hole correctly because I didn't anticipate the type of improvement we would have. I made the estimate based on the recommendations for typical geothermal systems based on an input of 5,000 BTU of heat into the ground continuously. But we're inputting something close to 12,000 BTU because of the increased efficiency. Didn't think about that. And so ultimately, for a system to operate as I had designed it, you probably need to double the holes. But to operate the system as I've demonstrated it, it still produces twice the temperature improvement or energy efficiency improvement over the original stock unit by a factor of 2 at equilibrium. So it's up to you. It's kind of like I did with the contractor. If you want to dig more holes, you can increase that efficiency back to the 12, 13, 14,000 BTU, or dig another hole and you can and dig another hole and you'll maintain very high efficiency, or stick with a single hole and you'll be fine at around a 10,000 BTU unit.
Yeah. It would be interesting actually to switching back to the boat a little bit, air conditioning on my boat, 16,000 BTU unit.
Yeah.
Of course, water cooled because it's got the
Right.
the
Plate.
lake right underneath it,
Right.
and
Is that a plate or is it pumped in and out?
pumped in and out.
Okay.
And when you have a weak through hole, it's pumped in and in. So that was just one
Wooden boat.
one of the recent problems that was rectified.
Wooden boat.
Yeah. Well, that was actually the plastic through hole, and
Okay.
yeah, which is now bronze. So, but just a curious question of, are those marine air conditioners, what's their relative efficiency in terms of power?
Yeah.
Mine consumes 1,500 watts at 110, 120 volts AC for 16,000 BTUs rated. And so it's got the good cooling. Because It's got the water cooling built right. I mean, that's the design. So,
Yeah.
but it's just a curious question now.
It brings up another point that somebody else brought up, and just interrupt me because I'll just go on and on. I love that air conditioner. But the point is, the fan was the biggest modification. And what I suspect is they sized that fan based on parts availability, cost, installation, contracts, a whole bunch of other things that we don't think about that aren't just based on physics. They're based on engineering, questions. But by removing that fan, there was such a tremendous change in the performance of the system that I suspect that another way to modify an air conditioner, rather than going into digging holes and doing the geothermal, is to fine-tune the two cooling airflow loops independent of each other. Because what I suspect is, based on the entropic argument, you want the outer condenser as cool as possible. So theoretically, you want that fan to roar if it didn't cost more in terms of electricity. On the other hand, the evaporator coil, by running at a very low temperature, even though you want your room at, say, 20 degrees Celsius, if it's running at 4 or 5 degrees Celsius simply to get the air into the room, it's kind of unnecessary. As long as it's running at a lower temperature than the temperature in the room, if that fan were roaring, you wouldn't therefore have to cool the liquid as far. So again, these differentials are where the overhead is coming from. And so I suspect that maybe the fan in your boat isn't optimized in terms of its blower function. But also, I think if somebody's looking at modifying air conditioners and don't want to get into the digging, you might be able to do a little modification in the shop by getting rid of the whole fan setup and introducing, say, controllable, inexpensive but controllable fans that allow you to tweak the speeds of each one of them for optimal output. Not too much energy into the fan, but good efficiency.
Yeah. Yeah, it's interesting. There are a couple of other YouTube channels that I've watched where they've actually switched away from the marine air conditioners to mini splits.
Oh, yeah.
Because the mini splits for the BTU output consume less power.
Yeah.
Even though it's now just a mini split sitting on the deck of a sailboat
Yeah.
with air blowing over it.
Right.
So now that argument that was given there was that the technology used for the marine air conditioners was designed to be robust and durable,
Right.
not necessarily efficient.
Right.
Interesting trade-off.
Well, that seems like that's the case. Like some of the bearings on that boat would be good for about 100 billion rotations.
Yeah.
And it's like, but the boat itself isn't going to last that long. That's part of the engineering balance. It's like you build it big enough so that everything breaks. Didn't you tell me that one? Where like
Yeah, right. Yeah. So, without naming auto manufacturers, right? You can look at some auto manufacturers who build some components that are never going to fail. And then they attach onto them a sensor that is guaranteed to fail at 30,000 miles. Right. And so it's a poorly designed system versus other manufacturers that think of the entire system and design it as a system that is expected to run for some amount of time. And then they haven't overinvested in some parts of the system and underinvested in the other parts of the system. So,
and if you have the ability to then add the next feature of how easy is it to replace the sensor? If the sensor busts every so often and is $5 and you can put it on yourself versus something where you have to tear the entire engine out to get the $5 sensor out that is screwing up the part that's going to last a million miles.
Have you looked under the hood of your car recently?
Nope, never.
There is no sensor that's going to be easy to replace or cost $5.
Yeah, right.
Yeah.
So, and that's part of the reason I think these air conditioners are built so poorly is that You want them light, you want them cheap, and you want them small.
Yep.
And so you compromise on airflow direction. And I'm sure that fan that I showed you in the video, I mean, that stamped out fan was about as bad an airfoil as I've ever seen. Just a simple drone airfoil is many times better. But again, that thing probably costs 60 cents, and the carbon fiber airfoil would cost as much as the air conditioner. So great engineering, but
Yeah, there are a lot of comments here about the dual inverter air conditioners now, where they are running inverters to control the fan speeds on both sides, and not even have fixed fan speeds.
Right.
And so again, getting to that question of in real time dynamically optimizing the airflow on both sides of the system.
Right.
So
I think that is the secret.
yeah.
And another mistake I made in that video is I guess a lot of newer air conditioners are actually now have returned to using the non-fluorinated hydrocarbons and are using propane.
Really?
It really works. Like every time you notice how effective propane is when you let it out of the tank and it's liquid.
It's nice and cold.
You can freeze yourself really fast. And when you think about it, yeah, it's releasing a C3 molecule into the air, but there's no fluorine in it, there's no chlorine in it, and so if it's even close to the same efficiency, that's kind of a nice deal. I like that. And I don't know if that was done for cost reasons or if that was done because of environmental regulations, but that was a correction. So I thank you.
Yeah.
Yeah. And then the other thing that we were looking at with the boat was your boat right now is powered with a diesel, or what are you using? And then you were going to do this conversion we're talking about.
So this is a little longer term thinking. So displacement of my boat, so the weight of my boat, 6,000 pounds.
Yeah.
It is running a Yanmar 4JH3E, 4-cylinder, 2-liter engine, 54 horsepower diesel. Super engine, very reliable, run forever.
Right.
It's 54 horsepower in a 6,000 pound displacement boat. It's not planing. It's not trying to plane. My friends have a 41-foot sailboat with, it's a different brand, but the same 54 horse motor. It moves that 22,000 pound sailboat just fine at 7.5 knots.
Okay.
So I'm way overpowered. And now, generally, I wouldn't complain about being way overpowered when it comes to machines and engines.
Right.
But it comes at the expense of noise. Not so much fuel consumption. It's a very thrifty engine, but it's noisy. And I've done a lot to try to knock that noise down to manageable levels, but it's still noisy. So the concept here is, can we switch this to an electric drive?
Right.
And
I like this.
Yes, yeah. So truthfully, 54 horsepower diesel right now. Looking at some of the research and some of the publications on test studies by different manufacturers that sell inboard electric motors, it looks like 20 horsepower is probably the number, and that's with room to spare.
Delivered horsepower.
Yeah, and that actually under my normal cruising, which is at about 5 knots, 5.5 miles an hour, I'm probably only need about 8 to 10 horsepower.
Right.
And so 8 to 10 horsepower, how many watts is that?
About 7,000.
7,000 watts. So 7,000 watts of power going into there. And just doing a little bit of the math on the weight of my engine. My engine's mounted backwards into a V drive, and the weight of 70 gallons of diesel fuel and all of the associated bits. And
let me just V drive, because I had to ask this question.
V drive.
Yeah, tell them.
So most engines are mounted where the prop shaft comes out the back of the engine, down through the hole, and propeller back here. In mine, it's mounted this way, and the propeller goes forward into a small drive that just is a V, looks like a V from the side, and changes the direction of the shaft from going forward to going backwards.
Why do they do that? It seems complicated.
Packaging.
Oh,
right.
Okay.
So in order to get either perhaps a shallower angle on the prop shaft, because if you have your prop shaft too steep,
you're trying to
just
push
trying
the butt
to
up the water.
lift the stern out of the water. So prop shaft angle, in this case on my boat, putting the engine in the exterior cockpit rather than the interior cabin. So
Right.
the noise is not inside the boat. So put the engine in the back, a shaft that goes forward and then comes backwards.
Okay.
It's another set of gears. So there's parasitic losses there.
Right.
It's another thing to maintain in terms of oil changes and another thing to break. That seems to be a reliable piece.
Yeah.
If it does break, I have looked up how much it costs for a rebuild kit for just the gears and the
Right.
bearings, $3,700. It's a boat, right? So
Yeah.
take any reasonable price and add a zero. So
Check out West Marine.
anyway, so 2,000 pounds plus of equipment that is that powertrain.
Yeah.
That's a fair bit of weight. And one of the things that I've also been just learning about and building a little bit is I live down in Florida, and every now and then we have a little storm that blows through and we lose power for a couple of weeks.
Right.
And so I've been putting together some lithium iron phosphate battery banks that will help keep a little window unit air conditioner going.
During hurricanes and
After a hurricane when we lose the power, right?
Yeah.
And so in learning about that, learned about these prismatic cells, they're called, and the amount of power density they have. And so the possibility for putting in roughly 60 kilowatt hours worth of battery capacity, a couple thousand watts worth of solar, and this electric drive, and I might still have all the range I need
right.
and hear nothing but the burbling of the water going by rather
Right,
than the diesel
exactly.
roar. So that's another project, and and another opportunity for collaboration for us, because I have a lot to learn about the motor controller,
Mhm.
the motor, not one that tends to want to just go buy a commercial solution
Yeah.
and be stuck with proprietary hardware that costs
Right.
a lot. So I'd like to understand that, and then all of this gets transmitted to the water through the propeller. And I'm fairly certain that a propeller designed for a diesel engine isn't going to be the right solution for an electric motor.
Depends on the RPM, obviously.
RPM,
Yeah.
torque delivery at RPM,
Yeah.
the speed that you should even be spinning the prop at that point, right?
Right.
You can probably spin a bigger, bitier, higher pitch prop at a lower RPM with an electric motor,
Mm-hmm.
taking advantage of its low RPM torque,
Right.
and not have as much chance of cavitation and whatnot. So,
Right.
So lots of things. Yeah. So
And in addition, because of all the electrical power, a lot of these other systems that you're talking about no longer require the generators, no longer require the alternator. And
Yep.
a lot of the other things where electricity is always an add-on, it's actually the core.
right.
So then you've got a bus that you're going to have to run through for your water cleaner, your air conditioner, or heater, depending on what you're doing, as well as the engine and all the electronics that you're using.
Absolutely. Well, and the benefit of going to a electric drive is instead of a 12-volt boat, because
Right.
everything's at 12 volts right now, minimally I would be at 48 volts,
Right.
possibly higher, but I'd like 48. And so at 40,
Actually, let me interrupt you for 1 second because
Yeah.
that was an interesting thing I didn't realize. But generally speaking, if you get a lot of industrial motors, they're like 220 is kind of, standard. And some of them you actually go to 308 and very high voltages. And one of the arguments is obviously you can use thinner lines, thinner wires, a lot less expensive copper to get the same number of watts into the motor. What I didn't realize is, why are they always dealing with these low voltages, super heavy cables, and super high amperage in boats? Like, why wouldn't they have the same thing? And then what you said about the sort of standard of, what was it, 52 volts?
So my understanding is 60 volts is a regulatory limit. And so these batteries that I just built with 16 cells in series,
Mhm.
3.2 volt cells, gets me to 52.8. They
Right.
call it a 48 volt
Right.
battery, but it's a 52 point something.
And if you went to 72,
You're at the point where, and you'd be able to answer this question better, that if you get touch those batteries and
Yeah.
create a short through your body, that's when you can start locking up muscles and be unable to release, right?
so you can put your fingers on each pole of a 12-volt battery, and we've all done it. No harm.
no harm.
You go to a 24 volt, you're still fine. But when you get to, say, around 60 volts, now the skin is not enough to
Right.
insulate you. And now your wet, mushy tissue is now a great conductor. And then
And apparently that's when muscles actually
Right.
seize up.
seize up, and then you can't let go as you're being
Can't let
cooked.
go. Yeah.
Yeah.
So
Okay.
48 volt, and that's why electric bikes, the electric bike batteries,
Have they been going up in voltage?
they've been creeping up,
Oh, okay.
but they're staying just under 60 volts.
Got it.
And I think there's a regulatory limit there where suddenly it becomes something that demands a higher degree of certification or some sort of thing.
Okay.
So
And the batteries you're using are actually only like 3 volts.
3.2 volt cells.
Right.
Yep,
Okay.
these prismatic cells. And lithium iron phosphate. I did see a comment here about big lithium iron battery equals boat on fire in icons.
Well,
So I'll,
stay tuned.
yeah, hopefully not. Lithium iron phosphate chemistry, as opposed to the lithium cadmium chemistry that we use in most of our batteries here in the United States. Most of the rest of the world uses the lithium iron phosphate technology. And in researching that, looking at that, that is a technology that I will just say is alleged and seems to have been demonstrated that it does not have the thermal runaway problem that a lithium cadmium technology has.
Ah, okay.
And there's lots of, find them YouTube videos of people taking the different cells and drilling through them, pounding nails through them and whatnot. And there's 3 primary types of cells. There's the pouch cells, and I believe early Teslas used pouch cells.
Okay, I don't know.
So it's a soft pouch that is holding the innards of the battery.
Plates, yeah.
And those are the highest energy density in terms of packaging.
Just make sure to be a little bit. Yeah.
Sorry. The highest energy
Everybody
density,
asleep?
yes, in the pouch cells, right? Because there's not a lot of structure around it. And then there's cylindrical cells that look like a regular cylindrical battery.
Battery, yeah. Okay.
And then there's these prismatic cells that look like these square aluminum boxes that are typically in blue.
So even though they call them prismatic, they're rectangle. They're rectangular boxes.
They're rectangular.
Okay.
Yes.
Sounds fancy.
Yeah. So the cylindrical cells are the most robust, and those, find the YouTube videos, run a drill press right through them, not even a whiff of smoke.
But they don't package tight.
Because they're cylinders, right? There's going to be some space loss there, right?
Yeah.
The prismatic cells, also robust, but a little more sensitive than the cylindrical cells. And so these are prismatic cells. They package very well because they're rectangular.
Right.
And you actually compress them when you use them. So that it's not a lot of compression.
Right.
5 Newton meters or something like that.
Yeah.
You tighten down the plates. But just enough so that as the chemistry inside wants to try to swell those cells up and down a little bit, there's a little bit of resistance to that.
Okay.
Now, again, lots of different channels that have run long-term tests with and without compression on these cells.
Yeah.
The manufacturers say compression. Lots of YouTubers and solar power guys run them without compression, no problem at all.
Right.
The difference is without compression and running 100% to 0% discharge, you're at 5,000 cycles.
Right.
We're not going to live that long. With proper compression and 0 to 100% to 20% discharge, 15,000 cycles.
Okay.
Long time. So
yeah. So is that it's probably not a chemical problem. It's probably a mechanical problem, right? Because when you think about it, it's like that movement isn't going to matter to molecules, but probably the electrical welding, soldering, all those sorts of things are stressed back and forth every time it moves a millimeter, you know. Yeah.
It's all down to the bus bars and the terminals on the tops of the batteries, right?
Okay.
And so if there's enough movement, then you start stressing those mechanical joints, like you said. So the bus bars on my batteries are flexible copper.
Got it.
And they have a little loop in the middle.
I see.
And the idea is that they can easily absorb that motion.
Yeah. Okay.
And they really do. So
so what's neat about that is the idea that what as you can kind of see, what we're doing is with the hurricane protection electrical, with the boat transition to electrical, with the water maker, electrical, some of the small little house, small boat, wooden boat, off-grid kind of applications that some of our videos have been sort of touching on with the solar panels and that sort of thing. We're going to try to get into sort of more real-world applications and testing of a lot of these things and integration to see, what we discover and what we learn.
Yep.
But not just sort of, we built this and it's been working for a month, this is what you should do and here's the recipe. But kind of like why we did each one of those steps and how we made that decision, so that when you disagree or you discover something better or there's been an upgrade, more knowledge or more better components are available, you'll know why and how. So if you're into into doing that, that's the kind of deep dive we intend to do on what seems like a relatively straightforward on the surface project. Is we really want to get down to the level of, where does it break and why, and then let's go 10% less and let's make sure we monitor.
Yep.
That kind of philosophy.
Absolutely.
Good
Yep.
engineering.
Right.
Yeah. Alex, I was just wondering if when we, keep answering these questions or whatever, I don't want to ignore questions that people have, even if they're not super chatting. If you see anything interesting, just interrupt me or
Sure.
something like that.
Most of
because-
these are related to what you're talking about. So if Lars sees something that looks
Okay.
interesting,
Yep.
just because I'm not as familiar with this as you
Sure,
guys are, so
okay.
I don't know if the question is something that is simple or I think
Okay.
that's better for you.
Okay, fair
But
enough.
if anything that comes in that I think is interesting related that you haven't addressed, I'll definitely bring that up.
Okay.
Yeah. Oh, Jeff S here definitely got the boat right. Break out another 1,000. Yeah. Let's see. There's still a lot more comments here about the lithium technology, right? The lithium. So mine, lithium iron phosphate are the batteries that I'm using. Iron, Fe, not lithium ion.
Right.
And I'm not an expert on this by any means. I've just started to research it for my own use here. And I did see a comment in there about the lithium iron phosphate batteries and their venting. The cells do all have vents on them. They
Yep.
are vents for when things go wrong,
Right.
not normal venting like you might have on a lead acid battery, right?
Right. And I'm not sure exactly what they vent. I'm assuming it's probably hydrogen. I'm not sure. But the point is, one of the other modifications we wanted to make, as you can guess, efficiency. One of the things that we were concerned about is we talked about this sort of high amperage, low voltage wiring system in a lot of boats and mobile applications. Is that because of the high currents that are running through these systems, you're less likely to get shocked, but you're more likely to get burned. There's heat. And the problem with heat is that metals' conductivity drops as they get warmer, probably because of the vibrations of the atoms inside. They're not as prone to transfer an electron, or maybe expansion. But the point is, you want to keep electronic components, almost always want to keep them cool. And so one of the problems with motors and the conductors to the motors and the inverters that are controlling the motors and probably even the batteries is that if we can keep them cooler, we may enhance efficiency. And so one of the things that we were considering doing is cooling these motors in order to keep all of the wiring as cool as possible. No mechanical modification to anything, just drop the temperature. And if you've got a 7,000 watt motor, typically these three-phase DC motors are about 90%, not typically, but if you got a good one, you get up to about 90% efficiency.
Yep.
So you're talking 700 watts into the container that's holding this motor. That's a space heater. And then you have the batteries themselves, which can grow warm during their operation, so that adds some additional heat. The inverters, the electronics, and all the we're probably talking a kilowatt is going into this part of the boat that obviously is not open to the air. So some of the higher power motors you can get are water cooled, Elco, submarine Elco, right?
Electric boat company.
Electric
Elco.
boat, Elco, yeah, right.
Yeah.
Electric. They built the first submarines during World War I or whatever.
Yeah.
Yeah, and anyway, they still make motors, and they're higher end, more expensive motors as you get into the 20, 30, 40 horsepower range can be obtained water cooled, which sounds like a great idea. But if you can get an inexpensive three-phase motor that isn't made for marine applications but can be used for this and cost 1/10 as much, it'd be nice to water cool it if you could. But one of the problems that we had is you want water flowing around a thing that can corrode and electrical conductivity and just water. And so we were thinking of using actually an air transfer mechanism to literally air condition or air cool the entire electrical system. And we're going to study whether or not does it count or help to add 50 watts for a cooling fan and a radiator and the pumps and that sort of thing, or is it actually just a waste of time and don't bother, you're not going to get it back. So that's another experiment we want to run with
Yeah.
just motors and cooling, because this could apply to your electric car, your electric boat, your electric scooter, golf cart.
Yeah, the Elco motors up to 20 horsepower, I believe, are 48-volt air-cooled.
Okay.
25 and up become 72 and higher, 96 volts,
Yeah.
water-cooled.
Yeah.
And so needing to manage that heat. So, yeah,
Yeah,
we'll see.
and we'll see. And the thing is, like, we don't stop. We say, could you use that hot air for something? You know, and then you just
Yeah.
keep going. It's like, how much can we squeeze out of every watt if we engineer it right? But don't get so stupid that, you know, eventually we end up with this $10,000 system to save, you know, 5 watts. There's a point of, you know, diminishing returns. But you don't know that unless you do it in real life. You really can't just do that on the computer, because the model is, I mean, the result is only as good as the model.
Right.
And the model is never as detailed as real life.
Yeah.
So,
Jim Bob's got a good comment here, right?
okay.
I was actually about to mention that, but I wasn't sure if it
Yeah,
was
All right.
I saw that
sensible
one.
or not.
Oversize your motor, size prop and gearbox correctly, you won't need cooling, right? And so the idea of not overdriving the working, the part of the system that's got the current flowing through it, right?
True. And I mean, the logic there is that obviously that motor was designed to carry, say, 100 amps, and you're running 50 through it. So it's not going to get as warm. And so therefore, it's going to remain closer to its optimal efficiency at 25 centigrade or whatever it is.
Yep.
But still, at some point, do you get a motor that costs twice as much because it's oversized and it's more efficient?
Right.
Or do you get the smaller motor that uses power as efficiently when it's cool, and then you pay that extra money for the cooling system? And I think that's the engineering alternative. You have to decide.
Absolutely. Yep.
You know, you don't want to build it any stronger than you need to.
Right.
And these things cost. Plus, there's cutoffs. You know, maybe you go up to 25 horsepower.
Yeah.
And it's like another 1,000, another 500. Then you go up to 30 and it's another 5,000. There's going to be break points where all these equations break down because all of a sudden there's a big jump.
Right.
You know.
Right. Yep. Here's a question back to the
Actually, yeah, if you
air
don't mind.
conditioner. Yeah.
Yeah,
Make sure you read it.
From FL Photo Catcher. Yeah, thanks. Because I actually thought about this myself before. But he asked, I would love to see a chest freezer made more efficient using a geothermal mod. Would that be as simple as using as the window unit mod?
Yeah. Again, I'm going to hit you with the engineering sort of aspect to it. I don't know what the power requirement is for that unit. That's easy to just check the tap, you know, the plate on the side. Because if it turns out, because of all that insulation, that this thing uses so little power, it's probably not going to be worth the effort to reduce its power requirement in half when it's using, you know, 10 watts. So I think what you'd have to do is you'd have to sort of first figure out, what is my power requirement now? Like, how much am I paying? Like, that's the first step in the engineering. How much am I paying? How often is it running? Or I could put up one of those integrating power meters. You can get the plug-in ones that not only measure instantaneous, but over a period of time. So you put it on for a 24-hour period or, you know, whatever, and then say, okay, I'm spending $1.75 per day in power. Now, when I look at my efficiency numbers, I'm going to be eating into that $1.75. And that's where you make the decision as to whether or not you want to go to a different, more advanced cooling system. It may be that just simply adding a cooling fan. Most of these things, I think, are just radiatively, you know, the hot air rises and the cool air comes in and it's passive.
Yep.
It may be a simple computer fan that's using a couple of watts, might actually, you know, double your efficiency or make it much more efficient because that coil in the back can get almost too hot to touch. And so if you keep that thing cooler for a few watts, you don't have to dig a hole, run any pipes or anything like that. On the other hand, if you got a big commercial freezer that may be using a couple kilowatts, that heat that you're dumping into the room then has to be air conditioned by another unit that you're paying power for. So it's multiple, it starts to add up. So first analyze that particular freezer, then look at whether or not, you know, it is running pretty hot. And then I think it would be relatively easy to actually just run an experiment yourself, try a fan on it, even a household fan, just blow it. You don't even have to mount it and get a controller and a switch, and see what happens to your integrated power. And then again, like I said, I don't know exactly what chest freezer you're talking about, but once you get up into the higher levels, you want to get that heat out of the room.
And Aza's built the code. Thanks for the 420. Back to the boat again.
Okay.
Make cheap thermoelectric generators and cover the boat? Question mark.
Oh,
Thermo-
thermoelectric, meaning the heat, the cool. I'm assuming what you mean is cool water, warm boat. But the boat isn't warm, so I'm not sure where would you get your heat from? You mean the radiator from the diesel, or where would be the hot source? If you want to put another one in and not pay for it, that'd be great. But I'm not sure exactly where you're thinking of the heat differential. The hard top is hot. One of the thoughts we had was that if he's got a whole bunch of solar panels in the Florida sun,
Yep.
those things run better when they're cooler. So if you can keep them cooler, that'd be great. But if you can't keep them cooler, use that heat as the hot side of a Peltier and use the underside that's the wind is blowing past as the cool side. You may be able to pump 20 or 30 watts out of that differential that otherwise is just completely free.
Do you have anything else about that, or should I?
No,
move
I
on?
think that's where I would go until
Yeah.
he clarifies about like what he was thinking about between the water and the boat.
Yeah. Okay. Yeah, and if he responds, I'll read that one.
Okay.
Yeah. Okay.
Aldrich, thanks for the 50. We're working on it. I have to look over the tiers again because we changed the tiers a few months ago. So I'll look over that and I'll make sure especially if you send us a message on Patreon, I'll try to get back to that one. But I'll just look over the tiers and make any adjustments that might be need to, and we will definitely honor any of the ones that are on there right now.
Yeah.
Thanks, though.
There's a good comment here from Rhett
Okay.
Oracle about the insurability of a boat that's been modified outside of its original parameters.
I know nothing about
That
this.
it's absolutely a real thing, and so ABYC codes, so American Boat and Yachting Council or something like that, is a organization, I guess. I don't know if it's a sanctioning body or whatever, that does set codes for everything from boat stability to electrical systems to fuel systems, everything. And so Rhett, absolutely to your comment, the batteries that would be used would be those that are already produced and meet AYBC codes and are UL listed as well. There's a number of different manufacturers that produce these marine-ready batteries. They don't package as nicely as they could be, or as tightly as could be, but they do have the benefit of internal fire extinguishers and being waterproof and a number of other things. All of these batteries, the lithium iron phosphate batteries, have these BMS battery management systems that are designed to address over temperature, under temperature, overcurrent, undercurrent, also not undercurrent, but all sorts of different conditions and manage those. And yes,
Well, one thing
has
that
to be done right, has to be done to code.
remember what you told me about the composting toilet?
Yeah. So another issue on boats, of course, is the toilet. And traditionally, toilets are either electric or hand operated, but use water. And it could be either fresh water coming from a through hole, or it could be, fresh water coming from your tanks, or it could be raw water coming from a through hole and is flushed into a black water tank, right? That's the traditional.
The black water tank is basically your sewage tank.
It's a sewage tank that you
Okay.
get pumped out at the marinas when you go in to refuel and get water or whatever you might get. So that's the traditional way. The newer way are these composting toilets, and even there's controversy about the word composting there
Yeah.
because the stuff isn't in there long enough to really
To really
compost. They're more-
bacterially deteriorate
they're
to
more
nothing.
desiccating toilets,
Yeah,
right? They
okay.
dry things out. Part of drying things out is separating liquids and solids, and so you end up with a bottle of liquids that is often poured over the side of the boat. And at least in the Great Lakes, the as I understand it, the regulations are that it's fine to pee over the side of your boat, but it's not fine to pour pee over the side of your
So
boat.
you can pee in a bucket, you can't throw it out.
Right.
But if you pee off the side,
All's fine.
all's fine.
So-
Okay. So regulations are sometimes quirky.
Quirky, yes.
Yeah.
But back to the idea of safety and doing any of this, right? Absolutely. There was another comment about causing injury with modifications on a boat. this boat doesn't move fast enough to cause injury. But
Right.
versus
I mean, you can't even get an electrical shock because, again, what we talked about before. You
48
can have
volt.
fires, but you can have
Yeah.
fires with diesel.
Right.
You know.
Absolutely. Yeah. Nominally 48 volts, but doing it right. And a big part of doing it right is understanding how much current is flowing.
Hmm.
And at a 48 nominal battery versus a 12 volt nominal battery, it's 1/4 of the current,
Right.
Which means sizing of the lines. Copper wire is super expensive now. All of that is something you have to do very carefully. All of the fusing
Right.
of all the different systems and fusing of the wires and making sure the fusing is correct for the gauge of wire. And of course, that the gauge of wire is correct for the load that you're going to use.
Right.
All of that comes into it. And it's never something that you want to just do yourself and not have a second set of eyes look over, experienced eyes,
Uh-huh.
have the boat properly surveyed by
Right.
somebody that understands these systems
Right.
and can do and is a
Right.
certified surveyor. Absolutely, all that needs to be done after any of these types of modifications.
Yeah, I think one of the things about these displacement boats, I like them because they're sort of pleasant. It's where you hang around on the deck with your martini and, you look at the scene going by. But because of the enormously low power to move a mass with these boats, they're all in the power range where a lot of us have the skills and the equipment to make them move. You can do this with a whole variety of different kinds of technologies. I mean, you can use a steam engine, you can use electrical, you can use diesel, and you can use. So it's a real fertile ground for doing the kind of work and modifications that ultimately, even if you don't do them, that precisely in terms of the hydrodynamic design and all that kind of stuff, whether it goes to hull speed, which is, and you can describe what that is, say 5 knots, and you really mess up and you go to 4.5 knots, you're still going to get there late.
Yeah.
But the point is, you're not going to get hurt from just high velocity impacts and that kind of stuff. So I
Yeah.
really like working with those.
Yeah. The most dangerous thing on a boat is a schedule. Because if you have a schedule to keep, then you make poor choices
Right.
about whether you go out into, how hard you drive the boat, things
Right.
like that, and then bad things happen.
Right.
So-
And that brought up a thing I was thinking about with like monitoring. At first I was thinking, let's monitor the systems. But one of the things that boats do is they bump into stuff, and boats can be run at night, and you have running lights and all these sorts of things. But I don't know how many boats are actively using sort of avoidance systems that are up to the current state of the art, like infrared cameras and LiDAR and these sorts of systems to allow them to sort of see themselves not just on a GPS map, but relative to the surrounding terrain. And I think that's another modification that I think would be fun to look into is sort of automated alarm systems, automated avoidance systems, using a more sophisticated but still kind of off-the-shelf stuff, not experimental. But you can get thermal cameras that aren't that expensive, and you can get LiDAR systems. I mean, they put them. How many LiDAR systems are there in a modern car?
Right.
It's like
Yeah.
distance measuring. Can we retrofit that kind of stuff onto a boat platform?
Yep.
That could be very useful.
Yeah.
And one of the things that you brought up was the GPS anchor situation.
Right.
Typically, when you set an anchor, I learned this through him, but typically when you set an anchor, you don't just sort of off the side of your boat, you drop this rope with this ball, this weight, this concrete block. Typically, what you do is with a bigger boat, you've got chain, you've got road.
Every boater in the world is cringing right now because anchors are highly engineered and rather expensive. Yes. So the fundamental problem is you're anchoring. And one of the problems or concerns you have when anchored, especially when there's any kind of weather,
Right.
is how well is your anchor set, and are you going to drag anchor? Meaning the weather is going to move you and your anchor, so you end up someplace where you didn't intend to be that might damage your boat or somebody else's boat. And so first step is make sure you have sufficient ground tackle, it's called, right? So the anchor is big enough and you have enough chain and enough the rope that attaches to that to put out enough scope so that you've got enough weight and mass on the seafloor.
Let me just interrupt you for one sec, because
Yep.
this is something I learned, and I thought, I never knew that. I always thought they had a chain on an anchor because it needed a strong connection.
Nope.
That's what I always thought. And then when I saw the chain attached to a rope, I thought, okay, they ran out of chain. But that's not the reason for the chain. It's not at all the reason. And I mean, you can describe it, or I can. But
We have rope because we ran out of money, not because we ran out of chain.
no, but the idea being that the chain actually provides the weight along the bottom
Yes.
that causes the anchor to dig in.
Right.
That's why you have the weight of the chain as opposed to a light rope.
Well, yeah. So the anchor. So when you're setting an anchor,
Mm-hmm.
and I'm not very experienced at this yet,
Mm-hmm.
so apologies, Greg and Alona. You'll drop the anchor and you'll back down on the anchor to actually dig the anchor
Okay.
into the base. Then once you've backed down on it and dug it in, you let out more chain and
Okay.
road. And the idea is typically in calm weather, you're going to have 5 times the depth you're in. So if you're in 20 feet of water,
Okay.
you're going to have 100 feet of chain and road out.
Wow.
And in heavy water, you might go to more like to 7 or 8 to 1.
And the reason being, you just want a much more, a smaller angle between the ground and the line that's going up, so that's pulling the anchor along the ground instead of out of the ground.
It's not even pulling the anchor. What's happening is with all that energy that's coming from the waves and from the wind,
Oh,
it's just lifting the chain,
okay.
right? And so you've got enough mass down there and it's far enough out that all of that shock loading is just moving that chain up
Doesn't
and
get
down.
to the other end
It
of the
doesn't even
chain.
get to the anchor,
Okay.
right? And that's the idea.
Okay. Sorry to interrupt.
Yep, no.
Okay.
So you want to make sure that if you do start to drag your anchor because the winds really come up or something like that,
Okay.
you have an alarm that wakes you up and tells you something's going wrong.
Right.
And those are all GPS based.
Okay.
And there's 2 issues with them. One that my friend Greg identified, which is you're setting the anchor at the front of your boat and you're pressing the button to mark the position back at your chart plotter on the back of the boat.
Because the chart plotter is what is receiving the GPS
That's
signal.
right.
So that's the point.
And probably your GPS antenna, which
Right.
is the true GPS point, is probably towards the stern of the boat.
Okay.
So you're already off, depending on the length of your boat.
And the
You know,
chain.
Well, yeah, depending on how far the anchor might fly on its way
Right.
down. You're off 30 or 40 feet already
Okay.
from where the anchor actually is versus where you marked it, which means as your boat starts swinging around that point at night, you're close to the edge of your allowed circle in one, and you're, way far away from it in the other dimension, 180 degrees from there. So there's the actual positioning of the marker point.
Right.
And then there's just GPS that can seem to have some vagary to it.
Well, actually, though, if this is your point, like if you have a single point and that's where you want to be,
Yep.
then in order for you to get up and deal with a problem, it's going to alarm if you go outside of that point. Say you got an inch outside that point.
Well, a point plus a radius is what you
Right.
set. And as soon as you go outside of that radius
Right.
from that center point, then it alarms.
But what happens if the boat is on the other end of the anchor? Because the center of rotation is not the center of your point. You've just
Right.
said it's a radius of like 200 feet.
Yeah. And
Okay.
that's part of the problem is when you mark that point, ideally you mark that point directly on top of your anchor.
Right.
But it's difficult to do that
Right.
just with the systems on the boat.
Right. Plus,
So
you got to know where it is.
you got to know where it is. So that's one issue. And since you're not directly on that point, and your mark is somewhere, if you imagine a circle, point is the actual anchor. Your
Yeah.
point is somewhere out in the body
Yeah.
of the circle, right? And so your boat can easily go outside the bearing or the edge of that circle
Right.
in one direction and be quite inside and dragging anchor
Right.
inside and still be
Okay.
inside the circle. So, and then it's all relying on a GPS. And so one idea is, could we use actually an inertial system
Mhm.
where we have these little gyroscopes on a chip
Right.
things, right? That are already included in a lot of the marine electronics,
Right.
and are included in an open source package that I'm going to start working with, OpenCPN. It's Open Chart Plotter. It has the little gyroscope on a chip
Right.
thing. I don't know what they're properly called. Apparently, extremely accurate, millimeter accurate. They're used to actually measure the heel of a sailboat.
So they're used for that purpose of acceleration,
Yes.
but underway to measure basically what the attitude of the boat is.
Yeah, right.
Okay.
So why not use that same set of inputs and just measure there inertially, not with the GPS antenna,
Right.
but and any vagary that might come from that, measure extremely accurately
Right.
how far your boat has moved
Right.
on anchor. That solves one problem of
Right.
just getting a more accurate measurement there. The other problem, though, is still that problem of knowing exactly where that center of the circle is.
Well, one reason that I thought about this, like from a sort of outside of marine application, is that you have to remember that GPS is constantly sending signals, so you may lose a GPS signal, but at the same time, that means you're resetting your positions continuously. All of these inertial navigation systems are based on sort of a 0 point of starting, like wherever you started.
Mm-hmm.
If they have any kind of drift over time, they can accumulate errors and never know. So they could drift slowly. Like I think they have not only a distance, but a distance per time that they can detect.
Yep.
Because the acceleration is still small, but after a year, you're a mile away.
Right.
But one of the things that I thought was kind of a broad application is that rather than using GPS, inertial systems, these chip-based systems have become so cheap. This thing will detect it.
Yep.
And it doesn't require any kind of GPS connection. So therefore,
Right.
it doesn't require radio frequency and wiring systems. It doesn't have the inherent error of the GPS system. And you could actually, because they're so cheap, you could put multiple ones in and sort of interrogate them to determine which one's the one in error. But you could place them in collars. You could place them in purses and wallets and keychains and your car if it's stolen, and all of these kinds of things that we're normally relying on GPS for. This might be a neat addition or a backup or a more precise, within periods of time, measurement of motion. And it'd be kind of a neat thing to be able to apply this. And again, if it's commodity level and with the electronic skill and some of the physics skill and optical skills, maybe we can build some of these things and try them out.
Yeah. Yep.
Yeah.
I didn't want to derail too much. If anybody was noticing a buffer, we lost some frames and there was a little bit of a buffer. So you might be delayed by a couple seconds, but it seems to be working again. Just something else that I saw, which was an interesting comment that relates to another project idea, and I think this would be great for the collaboration, is we got a comment from Hermie saying you could make a video with your ROV submersible showing what happens to an anchor.
That's actually a really cool idea.
That is
Oh, it's a good trip to Florida.
So, yeah.
Actually, no, to Michigan.
To Michigan.
Yeah.
The boat's up in Michigan.
We're all over the place.
Yeah. It is interesting. And
Yeah.
there's several different, well, there's lots of anchor manufacturers. There's several different philosophies, design philosophies around anchors.
Right.
And, but again, I don't have a ton of experience in this yet, but what I have heard is the shape of the blade of the anchor, the primary part that's going to dig in.
Right.
When you look at them, they kind of have some hydrofoil sort of looking
Yeah, they're
shape to them,
wingish.
right? And as you let them go, typically once, depending on
You're
whether-
just dropping it off.
if you just drop them or if you're windlass, the thing that pulls them in and out, freewheels them down, they can fall with some pretty good velocity and they can actually fly.
Yeah.
And so even though you're dropping them off the point of your boat, the bow of your boat, they could fly 10, 20, 30 meters depending on how deep you're dropping them.
It might
in.
be, what might be interesting there is the ROV not showing you where your anchor is, but show you how your anchor got there.
Yes.
Right.
Yes.
And what might be kind of interesting, again, another modification is, can you mess up that aerodynamic without messing up its structural? Because you can imagine, it's pretty easy to hurt a wing, to make a wing not work right.
Right.
And it might be that, for example, you don't want to twist it because this will probably, make everything screw up.
Yep.
But it might be in such a way that it just sort of falls because it can't get any lift. And how do you defeat that lift? I think I can think of a couple of ideas that you could use. And that might be kind of an interesting thing. It's like maybe modern anchor designs are not optimal.
While at the same time, not putting appendages onto the anchor that are going to cause it to get fouled and stuck on the bottom.
Right.
Or pull up excessive weeds or muck
Right.
or whatever.
Yeah, you
right?
can't get fancy. It's got to be robust and relatively
Wait, I saw keep it simple here.
convex.
Keep it simple, stupid, right? Is in
Right.
the comments here a couple times.
right.
There was a question here about marine wire. www. Recently got a deal on marine wire. Seems like it's just aluminum clad copper wire. Not aluminum clad,
Yeah.
aluminum would be subject to corrosion.
Yeah.
Marine wire tends to be copper that is, I think, tin clad, right? They always say it's
Right.
tinned.
Tinned.
Do you know, is that actually just tin, or what
I
is
think
the
it's tin.
It's just tin.
I think it's stannous. Yeah, I think
Okay.
it's tin.
And then that's
But I don't think it's pure tin, like
Okay.
regular solder often, with the rosins and everything. I think it's like, what is it? There's two components. Is it tin zinc? Like when they do 80-20, 70-30, what is
Right.
it? There's two lead. Okay,
Lead,
I think
yeah.
some solders are lead and it's like lead zinc. And then there's the other one. I'm not sure which metal. Maybe somebody can come up with it.
Yeah.
But it definitely is an aluminum. I'm not even sure you can get aluminum to bond effectively to copper.
Yeah.
You might.
Yeah, I'm not sure, but I just wanted to point that out that
Yeah.
the tinning of marine wire is to keep it from corroding. So it
Right.
certainly wouldn't be aluminum that it's
Yeah.
tinned in.
Right.
It's tin, it's
Exactly.
lead, things that are relatively inert metals that aren't going
Right.
to corrode. And so that's why in marine wire, it's tinned all the way through and through,
Not just at the ends
not
where
just
the
at
crimps
the
and the
ends.
solders and
Right.
everything.
Yep.
Right.
And critical for saltwater environments for sure. Right.
This is not true of, say, big, heavy arc welding cable. They're not tinned all the way along.
Not tinned. The tinning actually, my understanding is it makes it stiffer.
Yeah,
It makes
that's
sense
why
that
it's
it would
such
make it
nice.
stiffer.
Because I love welding cable. I mean,
It's beautiful.
I'm sure all of you do too.
Yes.
It's super. It's heavy, but it's very flexible. It's nice. You can coil it up and move it around. But some of that marine wiring, I mean, it's getting close to plumbing. I mean, some of the
It's
thick
pretty
stuff. It's like the PEX stuff that we showed you.
And being that it's marine,
It's
Four
cheap.
times the price of welding wire.
Right.
Welding wire, which certainly is designed to be super robust. So, in freshwater environments, can you get away with non-tinned wire? Not per ABYC, but probably. right?
Probably as long as you don't get an inspection.
Yes.
So we're not recommending that. We're not advocating that.
Not at all.
But but again, always experiment. One of the things that would be kind of interesting to do is taking your wire and somehow being able to analyze it. Like, can you use it in an environment for a period of time and then either sacrifice it because it's a short length and cut it up a little bit, peel off the material and see if it looks like there has been any corrosion.
Yep.
Another one is, why not recoat it with, say, a silicone type of coating so you can watch what's happening.
Yeah.
There's a number of ways, but I'm always sort of like, I like regulation because it keeps you from getting really bad ideas, but it also can kind of, force very high expense for utilities that are ultimately just repackaged,
Yep.
non-marine use.
Right.
So you got to be able to distinguish.
One little caution that I read about is that when buying wire from unknown sources, that you can actually plate aluminum wire with copper. So it looks like you're buying copper wire, but it's
Okay.
actually aluminum wire. Aluminum wire not nearly as
Yeah.
conductive as copper is.
Right.
Right. And so a cautionary tale for buying brand X wire with
But that
perhaps
one-
no branding on it.
That one's very easy. You don't even have to destroy
It's
it.
just the weight.
Wait.
Yes. When your package comes and it's
Yeah,
easy
it's easy to
lift.
move. Send it back.
Yeah.
Yeah.
Yep. So
Now, the buffering, Alex, we're fine. We can just keep
Yeah,
going?
buffering is
Okay.
fine.
All right,
I got
understood.
just recently a couple people saying that there was something like wrong with their audio, was like
Yep.
chopping, but a lot of other people are saying it's totally fine.
Okay.
So I just turned off the denoiser. I had it because we had the fans going before,
Okay.
but it should. I think it's fine anyways.
Okay.
a couple of comments about putting a device on the anchor itself to report its position.
I was actually thinking about that when we were talking, and the one thing would be communication.
Right.
And obviously, the chain in the road would be the sort of obvious way to do it, but you probably can't because it's not going to work. Something's going to get damaged and whatever. But it may be, I don't know if it could be done sonically. Communications through the water is excellent, and the amount of information you need is extremely low bits.
Sonar. So
Yeah.
So Bluetooth, I don't think would work at all because it's not going to transmit very far in
Mm-hmm. Right.
water. Other devices, super high powers,
Right.
in order to get a radio frequency through that
Right.
water. But a simple pinger
Yeah.
on the antenna that's just putting off.
Morse code.
There we go. So a little
That's
pinger
your
on
answer.
the antenna
Right.
and then a couple of sensors on your boat to triangulate
Right.
where that is.
And it can even be a frequency filtered ping, so that all the rest of the noise in the harbor and the clanging and this sort of thing, you work at a frequency that is unique and therefore your signal is going to be less likely to be interfered with. You probably can use less power and more range.
And have it only ping for 5 minutes.
Every-
5 minutes when you first drop it to position the anchor and know where
Right.
it is, and then it auto turns off.
Or cycles every hour to show that you haven't dragged your anchor.
Could be, yeah. Cycles every hour also, so that ever your line is parted and you leave your anchor on the bottom and your boat on top, that you do have a chance of actually finding your anchor. Because if you buy a good anchor,
Yeah, that's true.
So my boat, 6,000 pounds, 27.5 feet. The proper sized anchor is in the 20 to 25 pound range. A 10 kilo, 12
That doesn't
kilo.
seem that heavy.
Not terribly heavy. A commercial boat of my size would probably be sold with a 10-pound anchor.
Okay.
Right? They're always undersized.
Yeah.
My anchor new, I bought it used. My anchor new would be about a $400 anchor.
Wow.
Yeah. Get into the 41-foot sailboat that sits
Yeah.
next to me, and, now you're up into more of a 50-pound anchor, and you're at $1,000.
Yeah.
So these things are not something that you want to leave on the bottom of the lake if
Right.
you can avoid it.
Yeah. Yeah. I think the other thing that's kind of interesting too is, aren't there instances where like anchors will catch other anchors, like people, because if you're not out in the middle of the Atlantic, you're going to have a bunch of boats and they're all trying to, be polite and everything like that. But you've got a bunch of these anchor lines and anchors and a very confusing setup. There's a very good chance that you're going to pull on somebody else's anchor, or you're going to get tied up and you can't get off of it.
It's possible. It's got to be fairly congested for that.
Okay.
Not so much a problem in the Great Lakes. Probably more of a problem in Florida. Huge problem in the Mediterranean Sea. All right.
Just boat density?
Boat
Okay.
density. Yeah.
All right.
Yeah. Here in America, we anchor and we leave enough room to swing, and there's enough space.
Yeah.
In the Med, they do what's called a Med tie, where you drop an anchor, could be a stern, could be a bow anchor, and then you tie the other end of your boat to the land. And you actually end
Oh.
up with a bunch of boats that are parked like you park cars,
With ropes from the car.
with
yeah,
a lot
right.
of fenders. But now you've got a lot of anchor lines going forward.
Why did they do that? Just because of density of like
Density.
in the harbor?
Yeah.
Okay.
You're trying to stick. Watch the Formula One race from Monaco,
Right.
and you'll see a whole bunch of med-tied boats all tied tight together.
Maybe a stupid question, but why don't you put down 2 anchors? Not to be redundant, although that's nice, but you put a stern and a bow anchor, and they sort of keep the boat between the two of them. You're not going to be moving very much.
So that would be fine, and I will probably do that when I am in. So my boat only draws a little over 2 feet,
Okay.
meaning depth of how deep the boat sits in the water. Right?
Right.
So I don't need a lot of water depth, and so I can get in nice and tight in a cove,
Okay.
and I could put out a bow anchor and a stern anchor and keep my boat very well positioned,
Right.
and not be subject to wind and waves.
Okay.
My friends in the sailboat draw 5.5 feet, so they're going to have to be out further,
Okay.
potentially out where the wind and the waves are interacting with them.
Yeah.
And there, if you put down 2 anchors, bow and stern
Oh,
anchor,
and you can't move.
and you end up beam to the sea, meaning the waves are coming
Right.
sideways to you, it's going to be a
Better swim.
very nauseating night.
Yeah,
Right.
if you're lucky.
So bow and stern anchor certainly a solution, but only in very calm waters.
Ah.
Right.
Okay.
And then the other idea of 2 anchors off the bow.
Yeah.
Well, that means you've got 2 anchors, and now as your boat spins around those anchors,
You start
dozens
twisting
of
and-
times per night, you end up with the gigantic twist tie problem of expensive chain that you can't even pull back onto the boat because they're
It's funny when, like, I thought I came up with this great idea, and it's like, not only has it been tried, but it is well known to be stupid. But it's like, if you haven't done it and you don't live that stuff, you don't know it. So it's
Yeah.
like, you always got to be somewhat like humble about the fact that you think you know something about something
Yeah.
when you really don't.
Right.
Talk to an expert.
There was a question here: why don't airplanes have massive parachutes? Cirrus.
Yeah, I saw
Yeah.
that.
Yeah.
Yeah. And did you see recently one of them was activated and there was
Yep.
footage of,
Yep.
yeah, it's saving the
It
pilot.
worked?
Yeah.
Saved him?
Yep,
Yeah.
it did. Yeah, it was a midair collision. It was a airport that has 2 parallel runways,
Okay.
and they had 2 controllers operating the 2 runways, 1 runway each, talking on different frequencies.
Okay.
And-
To the tower?
so the tower had two controllers. They were each on a different frequency
Okay.
based on the runway that you were coming into.
Got it.
So the pilots couldn't hear the conversation of the
Between
other
them.
runway, right?
Okay.
And the runways. I mean, I was looking from bird's eye view, but they
Yeah.
were awfully close together.
Yeah.
And the Cirrus, I believe, kind
Yeah,
of
I have it.
overshot it.
Yeah, if you want to look up
Yeah, there we go.
Yeah.
The Cirrus overshot its approach a little bit and went into the path of the other runway and ran into a plane. Luckily, that other plane was a fairly large plane with no passengers. It was a ferrying flight,
Okay.
pilot only. No injuries. It landed normally. The Cirrus had to deploy its parachute. And
I don't think this is the same story.
Might not be
but,
the same
Yeah,
story,
but there's a few here that I'm seeing.
Yep.
I'm not sure which one. But,
Yep. So this is, I mean, this is a super high performance plane.
Yeah, I think it's one of the early designs of the super like carbon fiber, high aerodynamic efficiency airplanes
yeah,
that
super
fast and low power.
Super slick plane.
Yeah.
With that big parachute, and my understanding is that's saved hundreds of lives.
Yeah, it's kind of interesting. I don't know why other planes wouldn't use it, but I would think structurally you'd really have to kind of get pretty fundamental into the original design to be able to take the loads, because you can imagine when the thing is crashing, it's moving.
Yep.
And it's moving fast, and that parachute is designed to like move slow. So you're going to get a tremendous deceleration load, which is probably going to put G's on the pilot, which I'm sure he prefers over crashing, but it might, tear the loop out of retrofits. It may not be practical for many, other than maybe a Cessna 150
Yeah.
or something.
My guess is that parachute gets deployed once the wings have stalled, and you're moving fairly slowly at that point.
Yeah, but
Yeah.
that's assuming a controlled kind of,
It
like,
is,
you know
it
what I'm
is, it
saying?
is,
It's,
yeah. Yeah.
you're spinning,
Yeah.
that kind of thing. It
Yeah.
whips around and everything.
Yeah.
But, success is a great demonstrator, right?
Right.
Yeah. So, yeah, I don't know why a lot of safety things like this that have obviously worked don't become a much broader application. And I hope to heck it isn't anything to do with patents, because I think that would be a very invalid application of patents when there's a good idea that, gets other people killed simply because somebody else wants to make money. I'm not accusing anybody of it, but it has happened, obviously, a lot in the past.
Yeah. There's a
So-
good question. How do you avoid both aircraft and ship navigation collisions without radar and GPS?
Well,
So-
start from the beginning.
Well, start from the beginning.
Yeah, like, first of all, there's the pilot that is trying to, pilot avoidance, that kind of thing,
Well, right. So there's always that aviate, navigate, communicate.
Right.
Fly the plane first. Don't worry
Right.
about what else. Don't worry about
Right.
the wings. Amazing number of crashes from wings, doors that pop open.
Right.
And you get your attention is drawn to
Right.
dealing with the door. and
There's
you forget to
nothing
fly the
wrong
plane.
with that. It's just loud.
Yeah. But back to the boats for a second. My boat has GPS, yes, to tell me where I am. Does not have radar, but it does have an AIS, Automated Information System Receiver, and I don't have an AIS transmitter.
Right.
I'm looking into getting one of those. They're about $1,000. Maybe we can build a cheap one of those, right?
Right. Pretty soon, this boat's going to be worth a lot.
Yeah, or nothing.
Or you are not.
Or nothing.
Yeah, right.
But for those that don't know, AIS is boats can, if they have an AIS transmitter, they transmit fairly regularly, like every few seconds, their location, their heading, and their identification
Right. To the world,
to the world.
as far as it can be read.
To the world as far as the VHF
Right.
radio waves go.
Right.
And most VHF marine radios now have AIS receivers built into them and will display on their screen all the AIS targets.
Right.
So it has an awareness of all the different boats around you and their direction of travel, their rate of travel, and even the a $200 VHF radio will calculate likely collisions and sound an alarm to let you know that your rate of travel and direction of travel is going to conflict with somebody else's.
Right.
Sounds an alarm to alert you, and then I can tap on that target and
Right.
get their information, and then on the VHF I can call them by name
Right.
and identify it. Now,
And I think if this was sort of stimulated with the idea of like the anchor, the dragging the anchor and, running into things, obviously multiple layers are always good because each is going to have a strength. And plus, sometimes with the anchor, what you're going to hit isn't a boat. It's going to be hitting a rock or some other object that may not be identified on the chart. But then also the idea of if you've got systems like this that cover the same sort of ground but using different independent systems, if one fails or you can coordinate the two, you can then determine, I've got a problem. Both of them may be wrong, but something's wrong. I've got to investigate it.
Yep.
And I think once you bring the attention of the brain on the boat, the human, to this problem, you're probably much less likely than if you're asleep, you're down below, you're eating, you're focusing on your, whatever.
Who knows? Yeah.
So I like the idea of multiple layers of protection.
Yeah.
Yeah.
Yeah. And the aircraft equivalent is the TCAS system, which was pointed out here in the comments.
Right.
I didn't remember that, but do now that I see it again.
Yeah.
And the TCAS system, right, that collision avoidance system.
Right.
That
Isn't that only, though, for commercial? Like, I don't think non-commercial use that or are required.
are not required.
Right. It's
Yeah.
right.
Yeah. I believe military aircraft have it. Of course,
Yeah.
they can choose to turn it on or not.
Right.
If I recall, that military helicopter that collided with the American Airlines jet in D.C., the TCAS system has some altitude limits that
Below which?
it does not operate anymore.
Okay.
I guess because of ground clutter.
Yeah.
That would tend to give it too many false positives.
Right. It's
or
getting
false
near
negatives.
the airport and
Yeah.
there's 700 planes warming up.
And buildings and everything else like
Yeah.
that. Who knows what? But yeah, so I do. There's a channel, the Pilot Debrief that did a good explanation and understanding of all the different conditions
Right.
that came into that particular accident. But it's an interesting system for sure, and a good system, but has limits because of the noisy environment that the ground becomes
Right.
for aircraft.
I think one of the things that a lot of this sort of idea of electronics augmenting human abilities to monitor their boat. You don't have a night watchman in the crow's nest looking out for the pirates. So you end up having a whole bunch of electronics to take over for that. But I think also the idea is that a lot of this stuff is really a good idea, but is prohibitively expensive for wider application in things that we don't think about. That's why, we brought up with the initiation of this thing in the water system, is that can we use the advantage of consumer grade, which is often very good, look at your phone, consumer grade, but consumer quantity pricing, and make it therefore practical to use something that otherwise you wouldn't use, even though it's available, but you just can't afford it. There's just too many places to spend your money. And so I like analyzing these systems and deciding, how complicated really is that? Can we incorporate these kinds of functions?
Right.
And one of the problems that you get with a lot of the regulatory systems is that evolution of these systems are so slow because of the legal requirements and the liability requirements that it's almost like you are dealing in a lot of this 20 years behind the state of the art in what's possible. Again, think of what your phone can do compared to what your phone could do 20 years ago. And a lot of these aviation systems, I mean, I've flown in planes, I'm a pilot, I've flown in planes that look like they were built kind of when I was about 6 or 7 years old. And they use the same sort of systems because building the new plane requires all these regulatory testing standards and everything that make it impractical.
Yep.
That's why I think if we can empower individuals to be able to look at some of these things and say, we can apply, non sort of regulatory systems as long as we're not breaking the law. We're not
Right.
selling them to somebody. We're using them for our own purposes, but they're still usable.
Right.
You know.
Right. Did we even have phones 20 years ago? Maybe an actual phone.
Yeah, right.
Not a smartphone.
Yeah, right.
Yeah.
Something I had a question about, instead of the planes, but back to the boats. Do they make, because I saw someone here asking like a Tesla type, Jeffrey H., what about Tesla type auto drive to avoid crashes? Do they make anything for like non-expensive, like, multi-million-dollar yachts, but sort of like aftermarket?
Yeah, not like
kits?
yours.
Yeah. But aftermarket sort of like things or something you can build or, integrate with an existing drive system to be able to
Like an
either
autopilot on the
Yeah.
boat.
Yeah, but
Yeah.
autopilot, but it'll, direct itself to places, it'll avoid obstacles, things like that.
Well, direct itself to places, absolutely,
Okay.
and not particularly expensive.
Okay.
Still talking boats, so everything's expensive. But my boat has a Garmin system,
Okay.
and it runs on what's called a NEMA network. What's NEMA stand for? National Marine something Association.
Yeah.
Anyway, it's a protocol for communication. So it's the boat's wired basically with Ethernet, and so there's the GPS antenna, there is the autopilot, there's the chart plotter that has all the maps. Your radar can be integrated into that as well. There is an rudder angle indicator that's indicated into that. All of these devices throw what are called sentences onto the network, saying, I'm the GPS device, and here's my location. Throws it out there. Any device on the network that wants that information reads that sentence and takes it. And so boats already have autopilot, right? I can set a route. In Garmin speak, I can set a route and set a bunch of waypoints, and my boat will drive itself there. Now, it doesn't control the throttle. I set the throttle, and it just goes. And it makes all the turns. It corrects for any wind and waves and keeps me on track. I would imagine that certainly on the more expensive yachts,
Or even the more expensive Garmin's, like maybe the unit that you've got is just upgradable, or not to your knowledge.
it's not upgradable.
Okay.
It's getting on 15 years old now.
Okay.
I would imagine, yeah. So there are radar warnings, right? So I would think radar warnings and AIS warnings. Now, whether or not, I don't know the answer to whether or not the system can automatically respond to those warnings.
Right, to like avoid it.
To avoid.
Well, and you said it can't control throttle, but are there systems, the Garmin system, like different versions that could do that? So even if it can't necessarily avoid it, it could at least slow down, stop something.
You know, you would hope so, you would think so, but then also in my YouTube feed, pretty much weekly, I get to see something about a super yacht that's run aground because somebody fell asleep and it just ran itself aground.
What seems
So-
so crazy to me is like throttle control is probably so out of date. It's cables running to a diesel motor throttle.
Well, okay,
And therefore, how do you incorporate electronic control to a cable puller?
yep,
Okay.
Yep.
Electrically driven boats, trivial.
yeah. Which is another whole interesting topic. So my boat is cable.
Yeah.
You know, my throttle control
Right.
that does the transmission and the speed is just mechanical cables.
Right.
And NEMA stands for National Electrical Manufacturers
Association.
That is a different NEMA. NMEA is the one that I'm talking about. Marine something or other.
Okay.
Anyways, that was just a comment that came through. And so this is an interesting thing. So yes, there are electrical throttles, especially
Okay.
on outboards.
Yeah.
Outboards
That's
and
true.
things like that are electrical controlled. There are electric controls that are available for diesel engines as well, where the throttle that you're using, the joystick that you're using, you know, if you've
Yeah.
got a really nice Hinkley or something like that,
Yeah.
it's joystick control. It's all electronic. It's electronic to cable. So there are cable actuators.
So actually, the box where the handle is coming out is got an electronic thing electronic actuator thing.
Yes.
That's driving the cable, but it's still a cable to the engine. That's where the electrical.
And that actuator is typically in the engine bay. And
Okay.
we're talking, if not even just linkages, but
Okay.
2 or 3 foot long cables, right?
Okay.
But some of the yacht builders that build very nice yachts that transit the Pacific and the
Right.
Atlantic Ocean don't use those systems. They still use engines that are diesel engines that are the mechanical
Right. Throttle.
fuel pumps and
yeah,
throttles with cables
Right.
because electronics fail
Right.
a little more frequently, perhaps,
Right.
than those old mechanical systems. At least that's the belief.
Right.
And Nordhaven, that's what I was trying to think of. So Nordhaven yachts, beautiful, very expensive. They just came out with a 41-footer, I think. It's a true ocean-going boat. It's a beautiful boat. Uses twin Beta Marine 80 horse, I think, or so engines that are, if I recall right, not turbocharged, normally aspirated, completely mechanical diesel engines, mechanical controls
Right.
kind of bulletproof,
Yeah.
right? So yes, with electronics, you can start to do a lot of these fancy things and can have your computer say, I'm about to hit something, turn the throttle off,
Right.
go into reverse.
There's a couple of other things you could do. Impact imminent. Shut off the electrical system. Just turn off the motor. I mean, that's one very crude way, but at least if you have no velocity, odds are you're going to have a better result than if you need to go fast to get around something. So what I'm saying is, like, if you have a choice,
Yep.
I'd rather have no velocity. So one thing is you could just kill the engine electronically.
Right.
Okay, now you got to fix it or whatever. The other one is you could have redundant systems where you keep the entire mechanical system, but you have an electrical system that could drive in parallel with it. Your handles actually move, okay,
Yeah.
but it's electrically driven,
Yep.
and it's only one way. So when you function like this cuts off, so you're not fighting your
Right.
electronic system.
Right.
That way, I think you get both, and you could retrofit anything. And I think the electrical control would be great because it would allow you to do what you're saying, which is, say the wind picks up and you anticipate you're going to get there before the storm, and all of a sudden you're going to be 2 hours later than you thought. That's not a good thing.
Right.
So it would be nice to be able to control throttle, to be able to control direction, and also warn you when, we had to turn off your electrical
Yeah, when
system.
bad things are gonna
Yeah,
happen.
when bad things are going to happen.
Yeah.
Yeah, I do like the redundancy. Mechanical systems are great. Not being sort of the electrical engineer, I love mechanical systems because I can visualize them physically, and they rarely break once you fix them. It's like you first install them, they don't work. You install them the second time, they grind and they don't work well. And then when they work well, they last longer than you do. And mechanical is nice, but bulky, heavy, not adaptable to an AI-driven universe. So,
Right. Not dynamic in terms of.
yeah,
Yeah.
exactly.
Yeah.
Sailboats, aren't a lot of the high-powered sailboats, not necessarily the racing boats because of the standards of human interaction, but aren't a lot of them with their windlasses and a lot of their their line tightening engines, aren't they controlled from like the central cabin, like the cockpit? It has actually can operate these things. They're not all doing the grinding.
Yeah,
Right?
yeah. No, as boats get bigger, the loads on the lines
Yeah.
for raising the sails, things
Yeah.
like that, trimming the sails even becomes
Yeah.
so heavy
Yeah.
that you either need a highly mechanically advantaged windlass or winch,
Yeah.
or you need electric. Right?
Yeah.
And so they're electric, but those are always able to be run manually as well.
Right. But are they tweakable? So if you're sailing and you want to trim it a little bit and you want to tweak it a little bit, can you tighten, loosen, adjust continuously, therefore enter the computer and effectively maximize speed based on the computer program, and you're basically sailing an electronically controlled sailboat? Or are they all, again, very crude?
I don't think you don't sail if that's what you want. You buy a motorboat if you want to do that.
I bought a motorboat. It's just using sails in the process, too.
Sailing is all about the joy of tweaking those sails, right?
It's about the workload.
The workload of pulling up the mainsail.
Yeah, that's what
fine,
they
electric
say.
for that, right? But otherwise, it's
Well, that's why you need a young son, right?
well, yeah, young crew.
Yeah.
Yeah. No, I mean,
I get
the
it,
sailors
okay.
I know want to sail the boat.
Yeah.
right? And so they want to feel the pressure of the wind.
Yeah.
And they feel the pressure on the rudder. They want that
Right.
that feedback. I think much like people that are race car drivers don't want power steering.
Yeah, okay.
They want that direct feedback from the road,
Right.
from their car. They want that directness, right?
Right.
Versus us power boaters,
Yeah.
turn on the computers, let us know when we get there. We're going to go make a gin and tonic.
Yeah, right, exactly. Gin and tonic. I think it was designed for boaters.
Yes. So,
Let's see. Any other interesting questions or
question, what's dry docking during this retrofit going to cost you? My boat sits on a trailer, so no dry docking.
yeah.
And that's a whole nother philosophy that's out there right now. It used to be buy the biggest boat you can afford. Now there's a little bit of a movement towards buy the smallest boat you can live with,
Yeah. Okay.
right? And it kind of fits with that whole tiny house,
Yeah.
van life, live small.
Yeah.
You know,
Analyze your needs. and maximize your return.
within the smallest
Envelope.
package possible,
Yeah.
right? So my boat is 27.5 feet, I think, plus about 1.5 foot of anchor sticking off the front. Sadly, it's about 9 feet 2 inches wide,
Yeah.
which makes it
Road
whatever is
issue.
that 8 inches too wide for the
Without all
without
the-
a permit, right?
yeah.
Now I don't have to have a pilot car. I just have to pay $100 for a permit, and
Yeah.
I can have a wide load, and it's
Yeah.
barely wide, right?
Right.
But so there was a comment that made me remember that, right? But the dry dock, right? Yeah. So the fact that I can put my boat on a trailer,
Right.
my boat, as mentioned, cruises at about 5.5 miles an hour, 5
Right.
knots. Taking a really long time to get anywhere.
Yeah.
So, and I'm on Lake Michigan. If I want to boat over in, say, Lake Ontario,
You could through the waterway.
I could through the waterway,
Right.
and it would take me the better part of a month to get there. Or I could drive for a day and launch from a marina and be there.
Yeah.
Right. And
Okay.
so that's the flexibility that I have with my boat.
Right.
Because it is trailerable.
Right.
And it's trailerable with a 1/2-ton pickup. Right.
Right.
It's not some extreme heavy thing that I need a
Right.
1 ton or anything.
I
like
think
that.
also one of the things about like what we're talking about with this, with the dry dock and with the trailering, is that a lot of the stuff that we're trying to kind of get across is things that you can do. It's like, it's nice to learn about stuff, like I love watching starships launch, that sort of thing. I'm not going to build one. But the point is, if you're going to do a lot of the things we're talking about, once you get up to the scale where, for example, you'd have to dry dock or you've got $1 million boat, you're not going to go ahead and start trying to have fun with incorporating different kinds of systems. You're going to have so many other things that are going to be a problem. Number one, you've got enough money you can pay for these things, and you generally don't care. You're generally going to be probably a little less interested in the efficiency of the use of your money, but also just the scale of the things. The sizes of the components that you'd have to modify are so huge that I don't know. If you're interested in that kind of thing, you're probably not going to be interested in these kind of DIY projects.
Right.
Yeah.
Yeah. Absolutely. Yeah.
Yeah.
There was a good comment here about I like my where was it? My steel sails that are I like sailboats that use metal sails, the helix type propellers.
Ha ha ha.
Yes.
I guess I do too. See, I love being on a sailboat, and I've sailed Hobie Cats when I was much younger, and I really enjoyed that sort of a kick when the wind, really lifts the hull and you start to hear the humming and everything like that. That's
Yeah.
cool.
Yeah.
But it's almost like skiing or any kind of physical activity where you represent a substantial fraction of the weight of the whole package, boat and, human. Once you start to move into this scale where it's like Lars is talking about with 27, 30, 40-foot sailboats, the people moving around on it are minuscule in terms of weight. And therefore, it's like, then, I don't know, do you still enjoy the sailing as much when it's not that directly physically you don't get wet. If you're not getting wet when you're sailing, are you really having fun?
Yeah, you are. Yeah, and even on the 41-foot tartan that my friends bought, it's still a sailboat, right? So you're still trimming and trying to eke
Thinking
out.
and-
Absolutely. Looking at the angle of the wind, the trim of the sails, the heel of the boat, all of that to get the most you can out of that boat, right?
Yeah.
Yeah, when you get into Jeff Bezos' sailboat, not so much, right? That one's
Right.
computer controlled, to be sure.
Right.
Is it as immediate as my little Hobie Cat? No, not at all.
No.
Not at all. But it's still a much more engaged experience than
Yeah.
a powerboat is.
Yeah.
On my boat, once I set the route and autopilot is on, and
Yeah.
I don't have much to do,
Yeah.
so
Right.
there's time to read a book and things
Right,
like that.
exactly.
And luckily, there's not a lot of other boats out on Lake Michigan, so there's not a whole lot to run into.
Right.
And I'm moving far slower than everybody else.
Right.
So, all right. Anything else here on the comments?
Yeah, I've been looking through a couple of them. They're mostly just agreeing or making some jokes that you like portage.
Portage, yeah, that's when you
Yeah.
carry a boat over land.
Oh,
That's
okay.
portaging.
Oh,
It's a French
okay.
word.
Wasn't that when they
I
used
thought
to
it was
put the canoes on the, they've got the
Yep.
bark skin canoes
Right.
on them, right, the old
Yep.
paintings. Yeah,
Yep.
right.
Okay, that was
Portage.
really stupid of me. I actually,
At first, I thought you
actually
meant
thought
porridge.
no, I thought portage was a type of like booze alternate, like an old style, because people were making jokes about rum.
Pussers and
And
rum. Yeah,
isn't
right.
portage?
A Pusser's rum is the classic.
No,
it's
but portage.
portage?
Isn't portage?
Portage, I think, actually
pretty sure
also
portage
is
is
a kind of like very poor,
Am I wrong?
like gruel. I think it's not porridge. It's check it out. But yeah, I think they meant
Practice of carrying water.
let me interrupt for a second. So
Yeah, okay.
Arnie Carlson's commented on this a couple times. Lars is a Scandinavian name, and obviously you have some Viking genes. My father is Norwegian, from Stavanger, Norway. And
I'm 6'2", and he's one of the few people that I look way up to. In more ways than
not just
one.
because I'm taller. Yeah, so Viking genes, yes, and so Arne, another boat that my father and I have is a 1964 Norwegian Snekka, which is for those of you, which is to say everybody.
Is it
that
because it's a Norwegian boat
that what?
that you own it, or that he owned it? Or is it-
Absolutely.
Okay.
Yes. So a Snekka is a traditional Norwegian fishing boat.
Okay.
And so nobody will have known that. But it is, so they were made, the shape of the boat was largely determined by the timber in the area that the boat was being built in.
Oh, how much
and
you could
how
bend
much
it.
of a bend you could
Yeah.
put in it, right?
That's cool.
And so they're double enders. They look like mini little Viking ships.
Yeah.
They're held together with hand-pounded copper
Do
rivets.
the sort of
And not hugely
Okay,
flared
but
ends,
not a canoe.
But they're
Okay.
lap strake.
Okay.
And typically just finished with varnish. So
Yeah.
we've got a 23 foot.
and lap strake is this.
The boards overlap
Right.
each other, and the fastening is
Right.
copper nails
Yeah.
with roves and hand pounded.
Yeah, where you
rivets.
squeeze both sides. You're basically doing a nail into a rivet.
And you need a lot of bilge pumps.
Yeah.
So
So
Not
they
the
don't
ones-
leak much.
not the ones in Norway that actually that don't come out of the water every year.
They stay swollen.
They stay swollen and they're better maintained.
Actually, isn't it true you're supposed to like fill them with water or something at the beginning of a season, or you spray a hose on them or a sprinkler or something?
what we
You're
do.
supposed to wet them.
We swell it
Yeah.
up, and so I have one of those little flat green sprinkler hoses. You know,
Oh,
with
the
little,
ones with the
little
holes?
every
Yeah,
foot
okay.
or so, or 6 inches, and I weave that around through the boat, aiming out to the hole.
Okay.
Turn on the hose, come back 3 days later, and it's ready to put in the water. And it does a good job of watering the lawn.
I love that. That's great.
And when we launch it, now ours is it's a year older than me, so it's 61 years old, and because it goes in and out of the water every season and it's aged,
Yeah.
it leaks a lot more than
Yeah.
a better one that was well maintained and
Yeah.
lived a better life in
Cool.
in Norway.
Yeah. So you're right. Norwegian.
Yep. Yeah, a couple of the Norwegians on the live stream here tonight. So
Yeah.
that's
Yeah,
great.
you guys could get together and sync.
Oh well, it's only sunk a couple times.
Yeah, right. Yeah. So are there any other questions we should address tonight? I don't know, like if we don't want to keep people too long, but I'm willing to talk until midnight.
Yeah, well, we're getting near the end, so if there, I would probably, because we're at an hour and 52.
Okay.
So, yeah, I would say if there's any important questions or even slightly unrelated questions, this would probably be the time to ask them.
Now-
and then if you guys have anything else to...
Yeah, I want to, maybe I'll kind of round this out a little bit because we've been talking loosely here. What the plan is next Saturday morning, we're going to be releasing the next video, the standard videos that we do at 11 o'clock in the morning. So a week from today, but at 11 o'clock in the morning. We'll be hosting another live stream that evening at 6 p.m. Eastern Time. And I don't think we're going to have any other surprise guests next week, so it'll be Alex and me. We'll primarily discuss that, and we can discuss anything going on here. Lars and I are going to get going on this sort of water evaluation project, and I think what we're going to try to do is break it down enough so that we can kind of give updates that make sense. So, like, we'll get into maybe a material, like a consumer comparison, or maybe our water analysis system or something like that, to give you kind of an idea of things you might be able to use in the short term as we move toward the eventual implementation of the system. So off and on, I can't predict exactly when we'll get together again for that video, but we'll be doing other videos intermittently. And I think the next time that Lars will be here will probably be involved with one of the videos as opposed to the live stream, unless, you know, we follow up with the live stream.
Yep.
So that's kind of the round plan for everything. So yeah, thanks for watching, and thanks for putting up with our loose format. But it was fun because we've been talking boats and water and physics and engineering for the past 4 days, and my brain is starting to melt.
Yeah, and I like this format a lot better. And so, yeah, in the future, we're definitely going to have guests, but not always in person. But I think this was like a first good test, and I thought it was fun and successful.
Yeah, and I think if you did before, and I've written some of your recommendations down, if anybody has any other people that they think it would be good for us to communicate with, we're reaching out now. But, you know, if we can reach out to more people, we're going to get more choices, and we can do some more Zoom interviews about projects, interview people about a little bit about their history, and maybe argue about some point of engineering or physics. So thanks very much for watching. It was fun.
Yeah,
Yep,
thanks, guys.
This is great. Thanks
Yeah.
for inviting me.
Yeah.
This
Okay.
is great.
Yeah, thank you.
You bet.
See you later. See you next week.
Bye-bye.